and welcome to our recorded webinar. I'm Eric Farabee, the Director of Technical Services with the American Concrete Pavement Association. Today we're going to talk about PavementDesigner.org. I'm going to go through a little bit of the background of the program and go through some design runs. So let's get started. Now, PavementDesigner.org is a free web-based tool for designing concrete and cement-based pavement solutions. And there's a lot of freedom in what you can do with Pavement Designer. Pavement Designer can design for streets and local roads, it can design for parking lots and intermodal and industrial facilities. But within that, it can also design for jointed plain concrete pavements, continuously reinforced concrete pavements, as well as concrete overlays, any type of concrete overlay that you're looking to design. It can also design for roller compacted concrete pavements, as well as composite pavements that may use cement in some kind of modification of the substructure within the pavement section. PavementDesigner.org was developed for a number of reasons. The first is to address a need where city, county, and consultant engineers need a pavement design solution for designing concrete and cement-based pavements. Now, you'll see why this is important as we go through today's webinar. PavementDesigner.org, being a free tool, really kind of addresses that issue. Additionally, PavementDesigner.org was developed with professors and students in mind. Professors and students really need to be able to learn pavement design using the best tools that are available. And a lot of times, professors need those free resources to teach the students how to design the next generation of concrete and cement-based pavements. PavementDesigner.org, in addressing all of those different solutions for parking lots, streets and local roads, and intermodal facilities, as well as doing overlays and roller compacted concrete and all those other solutions, it is really drawing on existing design methodologies that were out there in various places, and it brings them all into one tool. And by unifying into this tool that's free and easy to use, it really makes concrete pavement design a lot easier for users. It's looking to fill that void. Additionally, in moving to a web-based platform, it's very easy to access, and since it's free, you have full access to the entire program. And additionally, if there are ever any updates to the tool, you can always access the most up-to-date version of the program without having to install any updates on your local device. This tool was developed in a partnership from the entire concrete pavement industry. The tool is developed by the American Concrete Pavement Association with industry partners of the Portland Cement Association and the National Ready Mix Concrete Association. Some additional support was given by the Roller Compacted Concrete Pavement Council as well. Now, as we discussed previously, PavementDesigner.org can address a lot of different needs from parking lots, streets and local roads, and intermodal facilities. And even within that, it can design for your conventional jointed plain concrete pavement, but it can also do overlays, roller compacted concrete, continuously reinforced concrete, as well as new composite sections where we're using some sort of cement modification for the substructure underneath a concrete or asphalt surface. It's important to note how these solutions are actually being calculated, what's driving these design solutions. And so this design map is kind of what we're going to follow as we go through today, but it's also going to show you what's powering the designs that you're actually doing. So when you're in these various modules, you can see which pavement design methodology is actually being used to power the solution. So let's get right in. Today we're going to start off talking about parking lot design, and then we'll go into jointed plain concrete pavement design, and then we'll finish up talking about intermodal design. Let's start with our concrete pavement parking lots. There are a few existing or old ways of designing concrete pavement parking lots, and those are listed here. So our first is our AASHTO 93. And we'll talk a lot more about AASHTO 93 when we get into street design with jointed plain concrete pavements. But for now, we'll just leave it at AASHTO 93. Additionally, there's a tool called StreetPave, which is actually featured within PavementDesigner.org. So StreetPave was an old desktop software that has now been moved and is incorporated and is largely the basis for PavementDesigner.org. And finally, there's design guides from the American Concrete Institute, or ACI. ACI 330 produces concrete parking lot design guides. The ACI 330 design guides feature design tables, so you're limited in what you can do, and you can see here what some of those design tables look like and what you're actually designing for within these. Now, all of these design tables are actually based on StreetPave and then the newer version on Pavement Designer design runs. So it's actually corresponding to what we're going to talk about today with PavementDesigner.org. Now, as I just mentioned, the old version of the ACI 330 design guides were based on StreetPave design runs. The new version of ACI 330 is based on Pavement Designer design runs. And PavementDesigner.org is largely based on StreetPave with a few minor modifications and updates. So Pavement Designer, when we do a parking lot design within the tool, is largely the same as what you'll see in the streets and local roads design when we're doing a conventional jointed plain concrete pavement. Now, the parking lot design module has been simplified slightly to make it specific to designing concrete pavement parking lots. And so you still have some flexibility in what you can do, but if you want a little more flexibility, you can actually arrive at the same design by using the street and local road design. We'll see a little bit more on that in just a minute. Let's go ahead and start designing with PavementDesigner.org and design a parking lot. And so for this parking lot design, we're going to design for a bus terminal that serves about 50 buses a day. And the only other information that we're going to be given is that the existing subgrade is a clay. Let's take a look at PavementDesigner.org. So here we can see PavementDesigner.org, and you can see that you're immediately brought into the tool, and you can actually start designing without creating an account or logging in at all. If you do want to create an account or log into an existing account, you can simply register for an account using an email and a password. That's all that's required to create an account for PavementDesigner.org. You'll see some of the other features that you can access when you create an account, but for now, let's just design without creating an account. Once we start a design, the first design selection screen that we're brought to is selecting the project type. So here we can design for our parking lots, our streets and local roads, or our intermodal and industrial facilities. Now, each of these tiles has a little flip screen that gives you a little more information on each of the designs listed here. When you look at these flip screens, you'll notice that the methodology that's powering this design module is actually listed here as well. So here, since we're designing for a bus terminal that's basically a parking lot, we're going to go into the parking lot module. Each of the design processes within PavementDesigner.org is broken into a 3-step process. The first step is our project level details. Next step is our pavement structure details, and the final step in our design process is the design summary. And that's where we can revise our design and determine if this is our final design or go back to the drawing board. Starting off with our project level details, the first information we need is a little information on our traffic. Now, within the parking lot design, we have 5 default traffic spectrums that we can choose from that refer back to the ACI 330 design guide tables. And so for this design, we know that we're doing a bus terminal, and the bus terminal spectrum would be ACI traffic spectrum C. You can see here when I select a traffic spectrum, my traffic summary details automatically populate with the axle loads that the pavement is going to be exposed to, as well as the number of repetitions of those loads per 1,000 trucks. The next step in my design process is choosing a design life. And so for this bus terminal, we're going to say that our design life is about 25 years. That's how long we want the pavement to last before we have to do some major rehabilitation or reconstruction. The next step is inputting our trucks per day. In this scenario, we were given that our bus terminal is supposed to serve about 50 trucks per day. So we can put in 50 trucks. Or 50 buses, excuse me. The next, we need our global inputs, which is our reliability for our design and our percent slabs cracked at the end of our design life. Since this is a bus terminal, it's a fairly slow operating facility, we can expect that our reliability is a little lower than, say, an interstate facility. Additionally, we can usually tolerate a few more slabs cracked in that type of facility before we would consider it to be failed. So maybe somewhere between 15 and 20% of our slabs being cracked at the end of our design life. Now, once we've input these details, we can move on to our pavement structure details. If we leave any of these inputs blank, we will not be able to move to the next screen. So let's move on to our pavement structure details. And here you can see that we need a little information on our pavement structure, starting with our subgrade, our concrete materials, and then our structural layers in between our subgrade and our concrete surface. So the first thing that we need to do is define our soil type. And in our problem statement, we were given that the existing subgrade is a clay soil. So you can actually see here that we've got 3 different types of soils that are kind of defined here. And we can actually select one of these in these options. And so here we see that we have clay-sized particles, which is why I selected it. You can see it automatically populates our subgrade CBR, or California bearing ratio value. And that gives us a resilient modulus of our subgrade. Now we can edit this as well if we know that our CBR is a little different. This is just a nice handy way to get at the end result of our resilient modulus of our subgrade. The next input that we need to deal with is our concrete materials. We have to define a strength of our concrete. And this can be done directly by inputting a flexural strength, or we can input a compressive strength, modulus elasticity, or splint tensile strength to estimate the flexural strength of our concrete. Now, since I'm designing this bus terminal, I may not know much about flexural strengths for concrete, but I'm familiar with compressive strengths, and maybe it should be somewhere around, let's say, 4,000 PSI for my concrete. So when I input 4,000 PSI for my concrete, you can see that it calculates a flexural strength for my design, 580 PSI. So the next step is defining our structural layers. Now within the parking lot module, we can have either 0 subbase layers between our subgrade and our parking concrete surface, or we can have 1. We can input a subbase layer in here. Now for this example, I'm going to say that we don't have a subbase and we're placing our pavement directly on the subgrade. So Pavement Designer calculates a composite K-value of the substructure, and then we can move on to our design summary. Now, similar to the project level details, if we do not complete every one of our input fields, we can't move on to our design summary. So once we arrive at our design summary, you'll notice that we're given a calculated minimum thickness and a recommended design thickness. Now, the recommended design thickness is basically rounding up to the nearest quarter inch. Rounding to the quarter inch to make the designer consider what happens if we go up or down to the nearest half inch. So here we can see we need about 8.19 inches of concrete to address the trucks that are given in this design. Here we've rounded up to the quarter inch. We could consider going lower, could consider going higher. We also have sensitivity plots. These sensitivity plots basically look at how the design changes with some of the more critical inputs that we've input throughout the design process. Our K-value, our flexural strength, our design life, reliability, and percent slabs cracked. So let's take a look at what flexural strength looks like and how it changes our design. So for this design, we were somewhere right in here around 580 PSI for our flexural strength. You'll notice what happens if we increase the flexural strength or we decrease the flexural strength. You can see how this design actually changes with that design input. So you can also look at design life if we want our design to last, say, another 5, 10, 15, or 20 years. We can look at what happens if we say we don't want 75% reliability or we want 80% reliability. We can also look at what happens if we specify less percent slabs cracked. And finally, K-value, defining the substructure of our pavement. So in addition to the sensitivity plots, we also have cracking and erosion reports. Now, the cracking and erosion reports are basically defining how our pavement is failing. And so you'll notice here that if we click on cracking, you'll see our total fatigue life consumed or total fatigue used. And we see we're almost at 100%. So that's basically saying at the end of our design life, we're expecting it to fail by cracking. And you can see that each of these axle loads that we saw in our traffic level details is causing a little bit of damage, consuming some of our fatigue life. Similarly, we have an erosion life, or total erosion used. And you can see we're nowhere near 100%. We're somewhere around 78%. And that basically means that our pavement is failing by cracking and not erosion. And so you can see here that we're not expecting the pavement to be completely faulted at the end of its design life. We're really expecting it to be fail by cracking. And finally, we have a little information on joint spacing. And that's basically describing how this maximum recommended joint spacing was calculated. So once we've completed our design, we can go back within this design process to change any of our design inputs. Or if we're happy with our design and we decide that this is going to be our final design, we can actually generate a report. And so when we click on generate a report, we can apply a little extra information that would go on our final report. So for this, I'm going to name it example project. You can leave these blank or you can input the extra details here. So once we click on that and finish our design report, you can see that our report automatically is generated. And now if you have a pop-up blocker on your web browser, this may not automatically show up. You may have to allow pop-ups from PavementDesigner.org, but you can see that it does generate and it actually downloads as well. And all of the information that we went through for this design is featured in the design report. You'll notice here within Pavement Designer that we also have this option to save. Now you will not be able to save unless you have an account with Pavement Designer. So you would need to log in to actually save this project. Creating an account is a free process. It just allows you to save your projects online and access them from anywhere. For this example, I'm not going to save this, but we'll see what that looks like a little later on. Some of the other things that we want to show you on PavementDesigner.org while we're in our initial tour is that we have a resources section and a support section. Within the resources section, there are a lot of good resources that relate to pavement design as well as construction as well. So you can see here we have a Pavement Designer intro video and a tutorial on how to design jointed plain concrete pavement. But we also have a lot of other resources related to various aspects of concrete pavement design and construction. All of these are free resources that you can access through the resources section on PavementDesigner.org. Additionally, we have a support section. The support section will bring you to a map where you can find a local expert on concrete pavement design and PavementDesigner.org. This will allow you to contact someone who's in your local area that can help you design concrete pavement solutions. It's a great way to reach out and get a little input on a design that you're working on. So we've talked a little bit about PavementDesigner.org's parking lot design. So let's get into our street and local road design. So within the streets and local roads design in PavementDesigner.org, we can design for a lot of different things. We can design for overlays, where we're looking at bonded and unbonded on asphalt or concrete or even composite pavements. We can also design for full depth concrete sections, such as jointed plain concrete pavement, typical concrete pavement, or roller compacted concrete or continuous reinforced concrete pavements. You could also design for composite pavements, where we're looking at some sort of cement treated or modified subbase or subgrade within our pavement structure. Now today we're going to focus on our jointed plain concrete pavement full depth pavements, which is our conventional type of concrete pavement. And so the other ways of designing the streets and local roads for full depth jointed plain concrete pavement are listed here. AASHTO 93 is probably one of the most popular ones that's best known around the world. And so we'll touch on that a little bit more and tell you why that may not be the best way for designing streets and local roads. There's also the tool called PavementME, or AASHTOWare's current design tool. That's currently the state of the practice for designing highways with concrete or asphalt. There are also design guides from the American Concrete Institute, similar as we had for parking lots. And then there's the Street Pave tool, which again has been incorporated into PavementDesigner.org. So let's go through each of these briefly. So AASHTO 93, as I mentioned, is one of the most popular and well-known pavement design processes for both concrete and asphalt pavements. It's been around for quite a while, as it was developed in 1993, but it also had iterations in 1986, 1972, and even in the early 1960s. All of those design guides are based on the AASHTO road test. They're wholly empirical, and they're based on that road test. Now, the AASHTO road test was performed in the late 1950s and early 1960s. It was basically a 2-year road test where we built these 6 test sections out of concrete and asphalt, and we drove over them for 2 years. Now, as you can imagine, with a road test like this, it's a fairly limited inference space. We have limited materials, structural sections, soils, traffic, and environmental data to see how our pavements degrade over time. So here's a little look at some of the structural sections that were analyzed on this AASHTO road test. And so thickness on this section wasn't really designed, it was kind of guessed. We tried a lot of different things where you can see we've got concrete on thick subbases, thinner subbases, even no subbase, where we're placing the concrete directly on the subgrade. So we tried a lot of different things, but we still were very limited in that we only had about 368 concrete sections and 468 asphalt test sections, with each of these being a certain length. Over the 2 years, we basically drove these trucks over the pavements continuously. And by the end of those 2 years, we estimated that we had about 1.1 million load repetitions of these trucks. So we basically looked at how our pavements were performing and degrading with the impact of these trucks driving on them and the 2 years of environmental information that we got from having these pavements in service. Now, another important thing to note is that all of this was done in central Illinois. So we had local materials to central Illinois. We were in an Illinois climate, and we were building these pavements on an Illinois subgrade, which is a clay subgrade, probably not the best for building pavements in general. So it's all good to know that there's a very limited inference space with this road test. So now at the end of the 2-year AASHTO road test, we had about 70% of our concrete pavement sections still in good condition. And now that's a problem because we have to predict how pavements are going to perform outside of this inference space, outside of those 1.1 million load repetitions that we had at the AASHTO road test. And so that's what they had to do to create the AASHTO design guides. So to illustrate that, we can take a look at what happens. So we have our known axle load repetitions, and that's our known inference space at the AASHTO road test. But now we have to predict what happens when we get outside of that inference space. This is one of the big problems with the concrete design methodology in the older AASHTO design guides, is that projecting outside of this inference space proved to be fairly difficult. And now we're designing pavements for significant more amount of load repetitions on our pavements, some up to more than 100 million load repetitions of our load repetitions being seen by our pavements. So we're well beyond the inference space of the AASHTO road test. And now some of these limitations of the AASHTO design guides are really noted even by the General Accounting Office of the United States. You can see this report is entitled Transportation and Infrastructure Highway Pavement Design Guide is Outdated. And so this is really why AASHTO moved and developed a new tool called AASHTOware Pavement ME. And so AASHTOware Pavement ME is really the state of the art for designing and analyzing pavement structures. It's really developed for highways, as it's developed by the American Association of State Highway Transportation Officials. And so now that's important to note because they really developed this tool for state agencies and federal agencies. And so it wasn't really developed for cities, counties, and towns and other types of facilities, which really make up a bulk of the pavements that are out there. So that gets back to the idea of providing a new tool in PavementDesigner that provides a good design solution for these cities and counties and towns that doesn't have the drawbacks of AASHTO 93. Now you may ask, why can't I just use AASHTOware Pavement ME? And the big reasons are it's fairly complex, as it is a very robust tool, and it is fairly expensive, as there's a yearly site license required to use the tool. Now, if you can afford that and you are a good pavement designer, it's a great way for designing really any type of pavement structure and looking at its performance. Now, if we take a look at AASHTO 93 versus AASHTO Pavement ME, you can really see that we blew up the inference space. So in AASHTO 93, where we had those limited structural sections, Pavement ME is based on test sections from all across the country. And it's really blown up what structural sections we have and really looked at a significant amount more of these structural sections based on the long-term pavement performance database, which is what AASHTOware Pavement ME is calibrated to, whereas AASHTO 93 is calibrated to one test section in Central Illinois. Again, blowing up that inference space, AASHTO 93 is based on 1.1 million load repetitions. Some of those LTPP sections have over 50 million plus load repetitions on them. Additionally, we're using materials from all across the country, not just materials from Central Illinois. And finally, we've got climate information from well beyond the 2 years of climate information that we have at the AASHTO road test built into AASHTO 93. So for all these reasons, Pavement ME is really a much more robust tool than AASHTO 93. Again, AASHTO 93 is wholly empirical based on that road test. AASHTOware Pavement ME is actually mechanistic empirical in that it's actually built on the mechanics of the materials to predict how the pavement's going to perform, and then it was calibrated to test sections all across the country. That's really a much more robust way of designing pavements. The next way that you can design concrete pavements for streets and local roads is ACI 325 design guides for streets and local roads. Now again, these design guides have static design charts where you can basically look at the design chart and figure out where you are for that design. These are limited design charts, and they were previously based on street pave runs. They are now based on PavementDesigner runs. So again, it will correspond fairly well to the PavementDesigner.org tool. Now, PavementDesigner.org, very similarly to Pavement ME, is a mechanistic empirical design approach for designing pavements. And so this was originally developed in the 1960s after the AASHTO road test was developed, and it was developed specifically for streets and local roads to create a design process for those. Now, the failure modes within PavementDesigner are cracking and erosion. This is a huge advantage over AASHTO 93, where the failure mode is present serviceability index, which kind of lumps all the stresses into one kind of black box type thing. And so actually getting to the failure mechanisms of our pavement and predicting those is really the best way for designing our pavements. And so with it being a mechanistic empirical tool and with it being free, it's a much more robust tool for designing pavements over the older AASHTO design guides. It's not quite as robust as AASHTOware's Pavement ME, as that is really a significant step forward in designing and analyzing pavements, but it's still a good, robust mechanistic empirical approach. Let's take a look at the street and local road design within PavementDesigner.org. And so here we're going to design for a municipal street. So our Overland Parkway, what we're designing for, has about 100 trucks per day. And the only other information we know is that it has an existing subgrade that's a poorly graded silt, or about an A5 if you're familiar with the AASHTO classifications. So let's take a look at PavementDesigner.org and try to design this pavement. So you'll notice here that we don't have the option to log in or create an account because we're actually logged into my account. And so you'll notice that here where you could have logged in, you can now see my designs. So I can actually save my designs within my account and access them anywhere. But enough on that, let's design Overland Parkway. So we start designing, and again, we have to select our project type. And so we already went through the parking lots. Now let's go through streets and local roads. So here you can see in our flip tile that we can design for jointed plain concrete pavements, which is what I'm looking for. You can also do those overlays, RCC, CRC, or composite pavements as well. So once we select our project type and we know that we're doing a street and local road, now we have to decide, okay, are we doing an overlay? Are we doing a full depth concrete section or a new composite? And so since we're doing a jointed plain concrete pavement, we're doing a full depth concrete section. You can see here JPCP is one of our options. So let's go in here. So now you'll notice that this looks fairly similar to what we saw within the parking lot design process. We have our project level details, our pavement structure details, and our summary details. The only difference is here we have a little bit more information that we need to provide to get through our design. For Overland Parkway, all we really had was that we knew we had about 100 trucks per day, and we had a little information on our subgrade. So we have a little ways to go in providing our design or creating our design. So the first thing is we have to choose a traffic spectrum. So I know that I have 100 trucks per day, but I don't really know what type of facility this is. Here, let's introduce the help screens. So you'll notice that this little question mark with help has been here the whole time, but it's been switched to off. So let's switch it to on, and you'll notice that whenever I hover over an input, I get a little pop-up screen. That little help screen is giving me a little information about that input. And if I click on more information, it gives me a lot more information on what I'm looking at with this design input. So I know I have 100 trucks per day. You can see here, if I look through and see my average daily truck traffic, 100 trucks per day fits in right about here. So if I look at that, I'm expecting that I should be in about a collector traffic spectrum. And so I'm going to choose a collector to be my traffic spectrum. So you'll notice when I choose the collector traffic spectrum, that my traffic summary details again update with my axle loads and my expected repetitions of those per 1,000 trucks. So the next input that I need is my design life. And this is really something the designer has to decide or the owner has to specify. And so here we're just going to say for this design example that we're looking at about a 30-year design life. Next thing that we need is our number of trucks per day. That one's easy. We're given about 100 trucks per day is what we're designing for. Next thing we need is a traffic growth rate. So if we expect this area to grow significantly, we may apply a modest traffic growth rate, say anywhere from 2 to 4%. If it's fairly stagnant, we may leave it at 1%. The next thing we need is a directional and design lane distribution. So this directional and design lane distribution is basically saying that if those 100 trucks per day are all in the northbound direction, as opposed to split between the north and southbound direction, I would say that 100% are in my northbound direction. Additionally, with the design lane distribution, if there's only one lane in my northbound direction for the trucks to be on, then I would say 100% of my trucks are in the design lane. If I have 2 lanes, then those trucks may be distributed between the design lane and the passing lane. So the next input that I need is a reliability. Now again, I'm not given much information on this, so I'm not sure what that reliability is. So here I can click on my help screens and get a good idea of what a good range might be for this type of facility. So for my collector type facility, you'll see that the range is typically somewhere between 80 and 99% for urban areas, or if I'm in a rural area, it may be 75 to 95%. So for this example, let's say that we want a reliability of 85%. And so similarly on the percent slabs cracked, let's just go straight to our help screen and see what the recommendation is. Collectors, somewhere around 15% of my slabs should be cracked at the end of my design life. And so when I get my traffic details input, you'll notice that we have calculated traffic results. And so this is giving me my average trucks per day in the design lane over the design life. So this is basically taking my trucks per day and applying this growth rate and the directional and design lane distributions and applying it over those 30 years. Now, it also calculates the total trucks in the design lane, basically taking this and applying it for 30 years and 365 and a quarter days per year. So with that, we can move on to our pavement structure. When we move into our pavement structure, you can see that we can design for jointed plain concrete pavement, roller compacted concrete, or continuously reinforced concrete pavement. So if I click on jointed plain concrete pavement, which is what we're trying to design for, you can see that we're brought to our pavement structure details. So again, we need our information on our subgrade, information on our concrete materials, and information on our subbase or structural layers. So here I know I have about an A5 subgrade, but I'm not really sure what that means again. So I can go ahead and turn my help screens on. And what would be a good resilient modulus value? Well, here we can see that we have our AASHTO classifications. I know I have about an A5 soil. So a CBR of 4 to 8 or resilient modulus between 5,000 and 8,000 PSI is really what I'd be looking for. So if I didn't have good information on my soils, I could look there, or I could find somewhere online that would give information on that type of soil. So I'm going to go with 5,000 PSI for my resilient modulus. So next information is information on our concrete. And again, we can define it a few different ways: flexural strength, compressive strength, modulus elasticity, or split tensile strength. For this, I'm just going to straight say that we need a flexural strength of about 550 PSI at 28 days. We can also input a modulus of elasticity, whether it be directly corresponded to that flexural strength, or if I have an actual modulus elasticity test, I can provide better information here, but it is defaulted to 4 million PSI. So the next option I have is to include macro fibers in our concrete. This is something that we're seeing a little bit more in concrete pavement overlays rather than full depth jointed plain concrete pavement, but it is an option featured here. Additionally, we can choose to include edge support. And so this would be an example, or an example of this would be, say, a widened concrete lane where we're building 13 feet wide and striping the lane at 12 feet to get that edge load, or to get those trucks away from the edge and reduce the edge load and edge stresses of our pavement. Another example of it would be a tied curb and gutter, or say a tied concrete pavement shoulder. If we have asphalt or aggregate shoulders, we would consider it not to have edge support. So I'm going to go ahead and assume that we have an asphalt or an aggregate shoulder, and we don't have a widened lane or a tied curb and gutter on this example. So next, we can choose how many subbase layers we have. We can either have 0, where we're placing our concrete directly on the subgrade, all the way up to 3 subbase layers in here. So I'm going to leave one subbase layer. I'm going to choose that layer to be a granular base. I'm going to say the granular base is about 4 inches thick. So when I do that, it calculates for me a composite K value of the substructure. And so that's basically taking our subgrade details and our subbase details and combining it into a K value. And so with this, while it's automatically calculated, if we do want to override it, we can override it with a user-defined input. Could say it's 175 PSI per inch instead of 260, and I could select my user-defined solution here. Or I could just go with the calculated K value from PavementDesigner. Then I can move on to my design summary. Now the design summary here has a fair amount of good information. You'll see the first thing that we are given is our calculated minimum thickness, and it's given for a doweled option and an undoweled option. And so this is basically saying what thickness is required if we're going to use dowels or if we're not going to use dowels. And you'll notice that sometimes these designs will be equivalent. And when they're equivalent, we know that our pavement is failing by cracking. You'll notice, as we showed in parking lots here, that when we're consuming the fatigue life or the cracking life of our pavement, then we're failing by cracking. And that basically means that while those dowels may be there and help reduce any erosion that might occur, they're not really providing a huge benefit on the cracking life, and so these designs are equivalent. That's not to say there won't be benefit from having dowels, it's just not the critical factor in this particular design. So we also have our recommended design thickness, which rounds that minimum thickness up to the next 1/4 inch, and then we have a maximum joint spacing. A lot of times pavements are designed to the 1/2 inch for constructability purposes, so you can see here that having that minimum thickness and showing that it's 7.54 inches and that design thickness is rounded up to the 1/4 inch, you may say, okay, well, my options are 7.5 inches or 8 inches. Here, 4/100ths of an inch, maybe we can round down to 7.5 inches. And so we have our same sensitivity plots where we can look at the impact of a changing flexural strength, a changing K value, which again, PavementDesigner calculated a K value of 260 PSI per inch, which is about 7.25 inches. At 175, we're about 7.5 inches. And so it didn't have a huge impact on our design, but we can look through these sensitivity plots as well. And if we do want to make a change, it's fairly easy to go back and make a change, like say changing my K value up to the calculated K value in Pavement Designer. And it will take a minute to update. You'll notice that my calculated thickness is updated as well. So we also have our cracking and erosion reports as discussed previously. You'll notice that our erosion consumed is fairly low as we are having a doweled section. If I click on undoweled, you'd expect to see the erosion consumed to be a little bit higher. And additionally, these are again dependent on the traffic spectrum that is used, as that's what the pavement is being exposed to. So different traffic spectrums will actually have a different impact on the erosion and the cracking that's consumed within our design. There's also a load transfer recommendation. So this gives you a little information on when you may want to go with the doweled option versus the undoweled option. Additionally, if you do have a thinner section, say less than 8 inches, and you do want to put dowels in your pavement because you want to dowel the pavement, it gives a little bit of a recommendation there as well. Additionally, there are other tools such as ACPA's DowelCAD program and additional resources from the National CP Concrete Pavement Technology Center that can help guide you in these choices as well. Finally, there's a recommended joint spacing. Again, this maximum joint spacing is calculated, and this is describing how that joint spacing was actually calculated for that output. Now that we've finished our design, we can either generate a report or we can actually save, since I've actually logged into my account for this example. So we can say Overland Parkway, and you can actually create folders within your tool, or you can save it to a default folder as well. So if I click Overland Parkway, and I'll even put a version on this, let's say it's version 1, I can click on save, and you'll notice that design was successfully updated. So I can go into my designs and I actually can find that example project that I just did, Overland Parkway version 1. So then I can actually, within those saved projects, I can go in and I can edit my design. I could actually duplicate my design if I wanted to make a small change and save both versions, or I can actually share a design. And so if somebody or someone you know has a Pavement Designer account as well, you could actually share the design with them, and then they would get an email and they would be able to access that design as well, and you could review it together. So if I share the design, project's successfully shared. And then finally, you can also delete these projects as well. So if I go back in and I can edit design, give it a little more information that would be featured on that design report, and I'm brought right back into my design. So that's our first street and local road design. Let's take another look at another design example. Now this one, I'm not going to go through and actually do a Pavement Designer design. I'm just going to show you the end result. So this is a highway design with Pavement Designer. Now we mentioned that Pavement Designer is usually meant for streets and local roads, but it can also be a good design process for highway design as well, just to kind of give you an idea of what the mechanistic empirical design might be for a highway pavement design. So this design example was actually based on an AASHTO 93 design example. And so the AASHTO 93 design inputs were actually featured here, and you can see what they were for this design. So we had about 20 million equivalent single axle loads, or EASLs, which is what AASHTO 93 uses to design, which relates to about 7,860 trucks. They required a 90% reliability with 5% slabs cracked at the end of their 20-year design life. They had a 6-lane facility, which those trucks were distributed out onto. There was also an R value, which is a way of characterizing your subgrade support, modulus of rupture of 630 psi, and an elastic modulus of concrete at 3.5 million psi. It was assumed that there was edge support and that there was an asphalt subbase of 1 inch, a cement stabilized subgrade of 6 inches, and a K value of 160 psi per inch. So the design with AASHTO 93 was 11 inches for this concrete pavement. The Pavement Designer design for this facility was 8.5 inches. And so that's a pretty stark difference between the AASHTO 93 design process and Pavement Designer. And so a designer could really think, okay, what does this actually mean? Why are they so different? And this gets back to the issues with AASHTO 93, the limited inference space, the limited number of inputs, limited information that it's actually built on, the fact that it's a little outdated, the fact that it's wholly empirical based on the AASHTO road tests, and the fact that Pavement Designer is a mechanistic empirical approach based on the mechanics of the materials and calibrated to actual design sections. And that's why it gives a much more realistic design. It's very much understood that AASHTO 93 tends to be overly conservative when it comes to concrete pavement design. But that still doesn't answer the question of, okay, well, how do I determine which one's actually right? And then we get back to PavementME, or AASHTOWare's new tool, which is really the most robust way of designing and analyzing concrete and asphalt pavements. You'll notice the design came out to 9 inches of concrete, very similar to what we have with the mechanistic empirical approach in PavementDesigner.org. And so here you can see the design reports out of Pavement Designer and out of PavementME. You'll notice here we have within Pavement Designer that my design is about 8.5 inches of concrete. And here in PavementME, my design thickness for my for my concrete is 9 inches of concrete. You can see PavementME actually has a lot more information here where it has roughness, faulting, cracking as they develop over time. So there's a lot of good information featured within PavementME that goes even beyond PavementDesigner.org. But again, it's fairly expensive, and Pavement Designer gets you fairly close. And that's what we're really looking for with the use of PavementDesigner.org. So we've got one more example for our street and local road design, and that's designing an equivalent concrete pavement to an asphalt typical design section. So this may be an example where an area is fairly used to designing or just building a typical asphalt section, say 4 inches of asphalt on an 8-inch granular base. The question kind of becomes, how do I design a comparable concrete pavement design when I don't have any other information in terms of what the traffic is or really anything like that? I just know that we typically do 4 inches of asphalt on 8 inches of granular base, and I'm looking for a 20-year design life out of that. With that, there is a way that we can do that with PavementDesigner.org. Let's start a new design and get back to our project selection screen. So we're going to go in. We know that we're going to build a concrete street that's comparable to an asphalt pavement that are given asphalt design. So we go in, we're going to do a full depth jointed plane concrete pavement street. We know that this was a residential area. That was one of my given inputs. So I'm going to say I have a residential pavement, and I know that I had a 20-year design life. And so those inputs are easy. But now we get to the traffic details, and this is where we really don't have good information. So how do we deal with that? How do we make a comparable input? That's where you'll notice we have this little drop-down menu. This little drop-down menu gives us an option to estimate our traffic from a given asphalt pavement design. So this asphalt pavement design is basically going to estimate the amount of trucks that our design will see over its design life based on the AASHTO 93 design process for asphalt pavements. We know that our given design is 4 inches of asphalt on 8 inches of granular base, so we know that we need 2 layers. We know that our reliability, again, if this is, say, a residential street, does not need to be very high, typically somewhere around 75%, a little bit lower than, say, a collector or an arterial street. And we know that our subgrade resilient modulus, this was another given, was about 4,000 PSI. So the next thing we have to do is define our layers. You can see here, the first thing that we have to do is an asphalt cement concrete. That's our surface layer. You'll notice it has a default layer coefficient of 0.44. If you're not familiar with these, you'd have to look it up in the AASHTO 93 design guide, but there is good information given in there on what these layer coefficients are. Drainage coefficients usually left as 1 if they're not good information. So we know we have a 4-inch asphalt layer on top of a granular subbase. And the layer coefficient for this is around 0.14 to 0.16, and that's about 8 inches thick. Now, if you are familiar with AASHTO 93, you can change the default design parameters. These are defaults given in AASHTO 93, so I typically leave those as is, but you can change terminal serviceability or anything like that to get answers more similar to what you might expect if you're well-knowledged AASHTO 93. But it does output traffic information numbers like the structural number of this design section, the flexible equivalent single axle loads, and the average trucks per day and the total trucks over the design life. And these are what we really need to do our concrete pavement design. So if I click save, it automatically populates those within my calculated traffic results. So the last thing that we need is our percent slabs cracked at the end of our design life. Now, since this is a residential facility, we can say probably somewhere around 15 to 20% of our slabs cracked at the end of our pavement design life. So next up, we can go to our pavement structure details. You'll notice that a few of these inputs, like the reliability, were grayed out. And that's because these inputs were featured within that previous screen where we defined our given asphalt design. So these are locked unless we go back to our project level details and change those within the estimated asphalt design. Now we need our information on our concrete pavement. So we again need a flexural strength or some other type of strength to get at our design. So here I'm going to say I have a compressive strength and I know that I want it to be, let's say 4,500 PSI, or too high, 4,500 PSI. Now, there are some checks within Pavement Designer where if we put in a value that's too high, a lot of times there's a red flag that will give you information that you're out of the recommended zone. So additionally, we need a modulus elasticity. It's defaulted to 4 million. We can have fibers or we cannot. We can have edge support or we cannot. And then we can have sub-base layers anywhere from 0 to 3. Here, let's say we have a granular base of about 4 inches. And it calculates our composite K value of the substructure. And we can move on to our design summary. You can see for this example, to get a 20-year pavement with our concrete pavement, we only need about right around 5 inches of concrete, fairly small joint spacing of about 9 to 10 feet as well. And you can see our sensitivity plots as well. So it's a great way to kind of get a rough estimation of what a comparable concrete pavement design would be if you're not given good traffic information. If you are given good traffic information, I'd really recommend going with that traffic information to design both the concrete and the asphalt to get a better estimate of what those designs actually should be. So there's our design of estimating a design based on a given asphalt pavement design. All right, so we've looked through 3 examples of street and local road design with Pavement Designer. Now let's take a quick look at the differences between the parking and the street design, since we mentioned that the parking lot module is very similar to the jointed plane street and local road module with some simplicity applied. So you'll notice in here that the differences between parking lot and street design is that we have limited structural or limited spectrums within the parking lot design. We may update that in the near future. Additionally, we have applied a traffic growth rate of 0% and a directional and design lane distribution of 100%. That means that all of your trucks are expected to, or that your pavement is being designed for all of the trucks that you specify. Additionally, we currently do not allow fiber use in the parking lot design, even though they may benefit your design within the module. It's really just applied there for simplicity's sake. Finally, edge support is assumed to be yes within the parking lot design module because most of these slabs within a parking lot will be surrounded by concrete, giving it edge support. And finally, we only allow 1 sub-base layer in the parking lot, typically because we don't see more layers used within the parking lot designs. So if you ever wanted to do a more robust parking lot design, but you wanted to deviate from these assumptions, you could use the street and local road module and do a jointed plain concrete pavement design and mirror these as much. Okay, so we've gone through parking and street and local road design. And the last thing we're going to touch on in this webinar is the intermodal design. And so the intermodal design, what are we really looking to design for? Well, here we're really talking about any non-over-the-road vehicles that our pavements may be exposed to. And you can see this is really meant for large container carriers or forklifts, really big industrial vehicles that don't have conventional over-the-road tires. If we do have an industrial or intermodal facility that's just exposed to say, semi-trucks and trailers, then that could really be covered in the parking lot design module and not get into this intermodal design. The intermodal design, again, is really for these over-the-road vehicles that have really heavy loads. There are a few other ways to design for these heavy and intermodal industrial vehicles, or the American Concrete Institute's 330.2R-17 guide for the design and construction of concrete site paving and industrial and trucking facilities kind of gets into some of those other tools that could be used for these types of vehicles and these types of trucks. You'll notice some of the software they recommend is ACPA's Street Pave program if you're designing mainly for trucks, PavementME, again, if you're designing mainly for trucks, a tool called TC Pavement's OptiPave tool, which we aren't going to really touch on in this webinar, and then ACPA's AirPave tool. Now, we mention this because ACPA's AirPave tool is actually what is used to do the intermodal industrial design within PavementDesigner.org. And so it's that tool that's really actually originally developed for aircraft, those really heavy loads on landing gears, that's incorporated within PavementDesigner.org. Now, PavementDesigner.org was released after this design guide was produced, and that's why it's not included in this list. So let's take a look at intermodal design within PavementDesigner.org. The first thing we're going to do is design for a CAT 986 loader. And you can see some of the details on that loader there. Let's take a look at how we actually design an intermodal facility for that type of vehicle. So here we're going in and we have to select our project type again. And you can see a little more detail on the intermodal design. You'll notice the non-over-the-road traffic. That's what we're really designing in here. We're not talking about, say, a trucking facility where we're really just expecting semi-trucks. Here, we're really talking about non-over-the-road traffic. Now, having said that, there's also a limitation in here that we're really only designing for pneumatic tires. We're not really looking at those steel wheel tires, and sometimes those plastic tires may not be applicable as well. You'll notice here that when we select the intermodal design, that we're brought immediately into the project level details. The main project level details that are featured here is what type of vehicle our pavement is going to be exposed to. You'll see here that there's a default library built into Pavement Designer for the types of vehicles that our pavement is going to be exposed to. And so we can select these default vehicles, and those will be the vehicles that our pavement is designed for. And so what we're designing for here is a CAT 986 loader, and you'll notice that that's one of the default vehicles. And so we can move on, or we can select that vehicle and move on to move further into our design. You'll notice that it's actually displaying what that vehicle looks like. It gives us a little information on that vehicle, the gross weight, its fully loaded weight, distributed on 4 tires, and the contact pressure, 90 PSI in a contact area. We'll touch on that a little more in just a minute. So once we've selected the vehicles that our pavement is going to be exposed to, we can move on to our pavement structure. And here we need to define what type of subgrade we have, our concrete materials, and our structural layers as well. Defining our subgrade, we can define it with a resilient modulus value, a CBR, or California bearing ratio, or an R value, or resistance value. We haven't done the resistance value yet, so let's start with that. And let's say we have an R value of about 15%. It'll calculate a resilient modulus corresponding to about that R value as well. So next we need our concrete materials information. So we're going to say that we need let's say that we need or are expecting a 600 PSI flexural strength mix. I'm going to leave my modulus elasticity at 4 million PSI. Now we can define our subbase layers. Again, we have a bunch of different defaults in here within our pavement, so we can try a lime stabilized subgrade or a cement stabilized subgrade, or even an asphalt layer or cement treated base, full depth reclamation. We can try all of these different things. I tend to like to design with a granular base, but all of those options are in there. They also all feature a default resilient modulus within there as well. So if you're not familiar with some of these, you can see what that might be as well. Finally, our layer thickness. Say we have 4 inches granular base. It'll calculate our composite K value, and we can move on to our design summary. So now the intermodal design looks a little different. We have our recommended design thickness, calculated minimum thickness, recommended joint spacing, and notice this new one, that's our stress ratio. Now the stress ratio given is 0.5%, and the general rule of thumb with designing concrete pavements is that if you design to a stress ratio of 0.5 or 50%, then you basically have unlimited load repetitions of that design vehicle, or in this case around 500,000 load repetitions, which is fairly significant. And you'll see that recommended design thickness is about 9 inches. We also have that familiar 9 joint spacing information to say how this maximum joint spacing was actually calculated. So additionally, within the intermodal facility, you can select more than one vehicle if your pavement is going to be exposed to more vehicles. And then you can move on to the pavement structure, and you can see which vehicle is actually controlling your design. Now, in future updates, we may incorporate a way to design to a different stress ratio or to a total number of load repetitions, but for now, it's designing to that 0.5% or a 0.5 or 50% stress ratio. That's one of the features that will be forthcoming within PavementDesigner.org. So last thing that I wanted to walk through before we finish up and call it a day here is some of those other design methodologies within that street and local road design. So if we go into our streets, we click on our overlay design, you'll notice that all of our design inputs are basically exactly the same as they were to that jointed plain concrete pavement. So we go to major arterial, 30-year design life, 150 trucks per day. Just going to go through and put some dummy numbers in here so we can see what this looks like, how we design for the various types of concrete overlay. You can see here that we can actually select which type of overlay we're doing, whether it's bonded on concrete or unbonded on concrete, or if we have an asphalt or composite pavement, we can do a unbonded or bonded as well. If we do click on the bonded on asphalt, we can access the BCOA ME tool, which is actually the best design methodology that's free for designing bonded concrete overlays of asphalt. So that'll take you to a separate site. If we go into the streets and local roads module, we already saw that if we go into the full depth concrete pavement, we have that opportunity to do an RCC or a CRCP pavement. And both of those designs look very similar to our jointed plain concrete pavement. You'll notice that the features are roughly exactly the same. There's just one note on using roller compacted concrete pavement, and that's that it's not typically used for high volume or high speed roadways, and that's primarily because of long-term load transfer. We don't usually put dowel bars in RCC. Additionally, with CRC, we note that you should really probably use AstroWare's Pavement ME tool because it's the most robust tool for designing that type of facility, especially with one that's typically as costly as CRC is because of all the steel. And finally, the last design methodology is those composite pavement sections, and those again look very similar to all of the rest of these and have that three-step design process. So feel free to explore those as well. And so with that, I would like to thank you for joining us for our PavementDesigner.org training module. Please use the site, and if you have any questions, you can feel free to get my contact information at the beginning of this presentation, or you can look on the support section within PavementDesigner.org. Thank you very much.